Hi everyone, it's me, Carrie. For 3 blind, is mean of 3 or average of 5 better? So I've tried to look into some of the math behind this, showing with these graphs here. And for those of you unaware, 3 blind is the event of solving a Rubik's Cube, but blindfolded. And for those of you unaware, there was a change to the WCA regulations in January 2026, taking the format of 3 blind from mean of 3 solves to average of 5 solves. Now, if you're going for an official mean or average on your WCA profile, to get that from mean of 3, you need all 3 attempts to be successes. Whereas with average of 5, you can have 4 or 5 be successes and you're allowed to have 1 failure. And that's because with averages of 5, the best and worst singles do not count. So anyway, which one is more punishing and which one's more nice between mean of 3 or average of 5? When I've talked to real cubers in competitions, those who are much more experienced with 3 blind welcome this change to average of 5 because let's say they're just going for a really fast single. Well, now there's more opportunities for a lucky single to show up because you have more attempts. And also, even if they are going for an average, I think that because they're more reliable, they just find that to be not that difficult. Whereas cubers who are beginners or just starting doing 3 blind, they find this change to be kind of punishing because they rarely get successes at all. So to go from having to do 3 successes for a mean of 3 to 4 successes for average of 5 feels like just that much more gargantuan of a task to ask of them. So let's look at some math here. Let's say R equals the success rate. So if you do your blindfolded attempt for 1 solve, you take off the blindfold, and you would say that like there's a 30% chance that the cube is solved after that, then we're going to say R equals 0.3. And we're also going to assume that all attempts are independent. I know they're not, but for simplicity, let's just say that. Now, I'm not going to go over these single probabilities because that's not really the part of this discussion. It's kind of simple. Let's just go with these 2 red values. So if R is your chance of success, and let's say your chance is like 1/10, you're not very good at this. Like most of the time you fail. To get a mean of 3, that's pretty simple. You just need 3 successes, and each one is a 1 in 10 chance. You just multiply them all together to get 1 in 1,000 chance that you'll get a mean of 3, and that's just R cubed. Makes sense. For average of 5, it's a little complicated because you have to include both the chance that you get all 5 successes, so that's R to the 5th. So now we're talking 1 in 100,000, but we also have to include the probability that you get 4 successes and 1 failure. So 1 failure is 1 minus R to the power of 1. 4 successes, that's R to the 4th. But then we also have to take into account the fact that there's 5 ways to do this, ordering wise. You could get fail, success, 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 or like success, fail, success, success, success. You get the idea. It's kind of like Pascal's triangle or the binomial distribution, whatever you want to call it. So it results in this number. So now the question is, which of these 2 is a higher probability given some success rate R? Like if you have a 50% chance rate, which one should you want to like sign up for if you really just want to get that mean or average officially? Well, here's my chart for this, plugging in all those numbers, and here's the graphs that show kind of it visually. So let's say your success rate is 50%. With that, to get a mean, it's just 1 out of 8. That makes sense. It's 0.125. To get an average of 5, you have 0.1875, which I believe is 6 out of 32. So it's a little bit higher. And obviously, as the success rate gets higher and closer to 1, so do all the rates of all the other probabilities they approach 1. But as expected, single sort of rapidly approaches 1. It's kind of like an ease-in function in animation software. Like very quickly, it ramps up, and it's already by this point, like 1/3, we're already getting 70% chance of a single, and then for average of 5, it's even higher, like 88%. So singles are just like easy now. But you notice that the means like start really slow and then only ramp up and accelerate near the bottom. Like you need to have an 80% chance of success to have a 50% chance of a mean and a 70% chance of average. But okay, so let's just look at the graphs. So you plug in your success rate on the bottom. The blue line is the identity, kind of just ignore that. But the single lines are on the top, which we're also not really talking about. The mean, so the green line is what it was for means, and the orange line kind of curving like this is the averages of what it now is. So from this perspective, it looks like the change just moved the whole line up, right? Like if you have a 75% chance, you went from here to you moved up. you went from like 42 to like 62 or something. So it looks good, but actually there is a crossing point. And okay, we could do it visually first or mathematically. It crosses at 0.25. Like you can see that. Okay, so this is the linear scale. This is what it truly looks like. But if you take a logarithmic scale like this, now you can see that green actually starts, no, orange starts much lower and actually scales up kind of exponentially. So at rates, if your success rate is lower than 1 in 4, then an average of 5 is actually harder than a mean of 3. And then if it's higher than 1 in 4, it's the other way around. Now averages of 5 are easier to get. And right at that inflection point, 0.25, I guess that's not technically an inflection point, that rate for both of them is 1 in 64. So let's look at some math for like how I got this. So you can see it just visually, but you know, it's not that hard to do the math. Like what you do is you just set these two equal to each other and solve for r, and you do that. And here's a crazy thing. I haven't been in like algebra class in like a decade. So when I was doing this, I'm like, whoa, this is like throwback to middle school or high school. And then like kind of like coincidentally, this equation, if you factor things out, gets you this quadratic formula, which can actually be factored into these very simple terms. Also, I should have kept the r to the third factor in there because r equals 0 is also a solution to this. But we don't really care about that. So it gives us these values where r equals 1 or r equals 1/4. We don't really care about 1 because that's also an endpoint. 1/4 is a point where these two sides of the equation will be equal to each other at 1/64th. And I think an easy double check for that is just to plug in 1/4. So for the mean, you take 1/4 and cube it, you get 1 in 64. It's the same as the size of a Minecraft stack. So that's like if you get a whole stack of dirt blocks and you pick one randomly, and then your friend picks one, the odds that you pick the same dirt block. And then if you do the same for the average, what I think is really interesting is you plug this in, and you're left with this one lone term that you can tell is going to be the smallest portion of the pie, and it's random like 5 and 3, and you're like, how are you going to get this number out of 5 and 3? Those are like odd numbers. They're very prime. But like what ends up happening is you have that 1 dangling, and the 1 plus 5 times 3 gets you to the 16, which kind of like factors, like it feels like that's a power of 2 that will like slot in very cleanly. So 16 over 4 to the 5th equals 1 over 64. I guess I could have just said 4 to the 5th is 1024, but it's all the same thing in the end. They equal out. So the moral of the story is that if you are a beginning blind cuber and your success rate is lower than 1 in 4, then you should dread this change that the WCA just did. But if you can get your success rate above 1 in 4, then this actually helped you. And what else was I going to say? I think one thing that's kind of interesting about these curves is that they look like general power functions. So like if you graph like x to the 1 and x to the 2, x to the 3, and also square root of x and cube root of x, it kind of looks like this, except for how the orange curve goes. Like the orange curve moves up and then actually surpasses the identity line, and it kind of asymptotically approaches 1. Like at values of success rate closer and closer to 1, like the average of 5 is even more exponentially close to 1. And that kind of makes sense because you're allotted to have 1 failure. So if your success rate is like 95%, you still will basically almost always get an average of 5, because in order to fail it, you need to get 2 failures in 5 attempts. But if your success rate is 95%, that's just not going to happen. Whereas with mean of 3, it's still decently likely that there will be a DNF that sneaks in there every now and then. So it's kind of just an interesting way that like this graph looks almost like those power functions, which kind of looks like a leaf shape, except for this weird crossover, which I think is interesting. That's basically it for this video. And I think if you are a beginning blindfold solver and you are sad about this, so a few things, like one, I don't know, I feel like a 1 in 4 success rate is like a decent goal for people to try to get to. The other thing I want to point out is that I know that people also mention there's time limits and cumulative time limits. Like if you're only allowed to take a total of 10 minutes or 15 minutes for the sum of all your times for a round, then you may go over that limit and then be cut off quickly when it comes to doing 5 solves versus 3. And there, I think you are correct. But maybe organizers can just give longer time limits. But I know that's not always possible because the day only has 24 hours. So I didn't really include that in the equations. So sorry about that. The other thing I was going to say is that from the beginning, we are assuming that these rates are independent, which they're not. And this is kind of like relatable for myself because I was just at a cubing competition today where I was trying to go for a average of 5 and I got 3 successes in a row for my first 3 attempts, and then I kind of psyched myself out, got a little nervous, and then I got 2 DNFs. And I think that there is a case to be said that like if you're on a good streak, for some people that would actually increase their chance they succeed at the next one because they're like hyped up and they're putting in more attention and focus on it. And for some people, more people I would say, they get more nervous and they start shaking or like a second guessing themselves, and then they actually fail more often. And I don't know how that would affect these numbers. I feel like that's just not like that clean to slot into the equation because I don't know, the way that nerves affect you is not like a mathematical function. It's different for each person. But I just wanted to add that there too, because I'm sure some people will say like, oh, you can't just assume that like bam, 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 all 5 results are equally probable. But yeah, I think this graph is interesting. I'll put it in the I'll put a link to this in the description of this video. Yeah, I just want to make sure that my little webcam is not covering anything up. But these are beautiful curves, aren't they? And yeah. Don't forget to learn algebra in school, kids, because eventually when you are a cuber in their late 20s, you will be doing this too, I guess. Okay, thank you for watching this video, and goodbye.